Set the focus.
All right, any questions? Then why do I have these quizzes in here? All right. We last left off where we talked about the different types of waves, the longitudinal and transverse. Let me comment about two other types of waves that are not really a concern for us right now. But, so we had the longitudinal, and I think those were the only two that I talked about last time. There's a third type of wave, third type of mechanical wave, I should say, and let's specify these are mechanical waves. And the fact that there's physically an object that is moving in order to create the waves. There's a third type that I don't see very often in textbooks, but occasionally I do, so just in case you run across it. The third one is a surface wave. And one reason why it usually is not given in the textbook is it's just a combination of the other two. In the ideal surface wave, if you think about an ocean wave coming in, sort of that rolling wave, not the one that's breaking on the surf, that the particle of water is basically going to be traveling in a circle. So as the wave moves to the right in this example, the particle of water just sort of moves with it for a little bit and then gets sucked under and then comes back up. And so there's some movement that is in the direction of the wave, some movement that's against the direction, and some that's transverse. So it's just a combination of the other two. And then the example of the wave which is not a mechanical wave is the electromagnetic wave. Which I believe the textbook gets into in chapter 25 or so. In that one, that does not require a medium. There's no physical particle that is moving. It's an oscillation of the electric field and the magnetic field. Matter of fact, that was one of those things that the physicists made up, and it took another 60 years before they finally found evidence that it really existed, which is why it shows up in textbooks today. So when I draw up a wave, no matter which kind well, throw that one out. I have the same basic look of all the waves when I actually draw it on the board. It just means something slightly different. If it's a transverse wave and I draw something like this, that would be more the physical representation of it. So if I have a long coil here, or if I have a cord, since that's what I have easy access to, and I create a transverse wave in it, that would pretend that this would look like that. This would be a physical representation of what that wave looked like. As in, that was the shape. Longitudinal waves, I'm still going to represent the same way, except it represents something slightly different. So if I'm talking about sound, I've got my vocal cord sort of vibrating back and forth, and it's pushing air molecules closer together. It's making air molecules farther apart from each other. So this would represent a point where I've got a bunch of molecules really close to each other. And then some points where they're farther apart, and then points where they're really close to each other again. and as some of you probably know at this point, this is known as compression. And the plate where there's fewer than normal is rarefaction.
That's how sound travels?
Yes. That was a multiple choice one, right? On the master set?
Oh, I don't know.
Oh, not particularly crucial. I think
Oh,
I had.
yeah, it is. It's number 3.
So was that, I had compression, rarefaction, both or
And
neither?
neither of these. You had compressions, rarefactions, and neither of these.
Okay. So just make sure you put down A and B. And there was one of them where I had those two and then both as a separate choice. And then the instructions is check all that are appropriate, which means you would check A, B, and C. But apparently I corrected it for that. So if the case of examples, you could treat it as sort of density of air, but typically with sound, this would be high pressure and low pressure. That was that sad marker, so this one does. Now, even though when I'm talking about sound, this is what's closer to the physical reality of particles getting close to each other, it's not easy to draw all the dots, and so I'll still draw sound this way. There's a third way that I might represent the waves, and that's sort of the overhead view. If I throw a rock into a pond and you get that ripple going. So I could also represent sound by a series of lines like this, or in this case right here, you put it basically where the high pressure is. So this represents high pressure. Usually with an R in it. And then between the waves would be the low pressure. And this is a useful way of doing it when you start talking about Doppler effect or get into sonic booms.
Is that arrow pointing to the line or outside the line?
This is pointing to the line. High pressure points to the line. This is pointing to
The middle.
between them. That empty space in between. Questions at this point? About to do a couple more vocab words and then get into some more meat of it. All right, there are some common terms that show up when you're dealing with waves. So let's start out with those. Or continue with those. And actually, these work regardless of whether it's a mechanical wave or an electromagnetic wave. Or the oil wave would be a mechanical one. Period. So when you're talking about cyclical motion, so something that gets repeated over and over again, period is how long it takes to do whatever you're doing over and over again, how long it takes to do it once. So when you were swinging the stopper around for the centrifugal motion lab, the period was how long it took for it to go around once. So you timed it 20 revolutions divided by 20, and then you figure out the period. The symbol for period is a capital T. It is the time to do one cycle of repetitive motion. And as such, the SI unit, well, it's time. So what is the standard international unit for it?
Seconds.
frequency. Symbol F. If you watch the video, which presumably you have at this point, there is another alternate symbol for it, the nu, which I won't, well, let's discuss it in the video, I'm not going to go over it here. But there is another symbol that's often used, but I use the F. The same kind of F I make when I'm talking about friction. Because, again, we've used all the letters. Got to start repeating them. So frequency is how often, or how many times. Repetitive motion is repeated. In some time period, usually per second. Although it depends upon what you're talking about. If you are listening to an album, a record, that generally is in per minute. So period is the number of cycles per, is the time per cycle, and frequency is the cycles per time. They're just flips of one another. So frequency is just the same, is just 1 over the period, or period is 1 over the frequency. They are multiplicative inverses of each other. So the units of frequency would be the units of basically cycles per second. However, that's not the one word. What's the one word? The one word unit of frequency. Hertz. Named after?
Hertz.
I believe Hertz was the man who actually figured out that the electromagnetic waves really did exist. Or came up with the experimental evidence for it. Two more of these vocab words, wavelength. The symbol for wavelength, the lambda. And this is how far a wave travels. In one period. So if I've got battle ropes attached, and I got these two big ropes attached to the door over there, and I start going up and down like this, the period is how long it takes for my hand to go from here to here and then back to where I started. Not just, so if I'm starting in the middle, the period is not from here to here because I'm going in the opposite direction. So basically I want to get to the same point in position and velocity. So I'll go from here down and then back up, that would be the period. And then how far that ripple traveled would be the wavelength in that amount of time. So since it's answering the question of how far, what would be the unit of wavelength?
Meters?
Yep. And then the last one. Amplitude. Amplitude is just basically how big. I mean, there's a difference in the amplitude, again, going back to, I'm assuming people know what battle ropes are. I'm trying to get some recognition. You got a couple people who know, and just stares from other people. Exercise equipment, you got a long, like, is it a thick rope? Okay, it's
Really
a thick
heavy.
rope attached to a wall, and then you get exercise, presumably mainly your arms.
You do it squatting, though.
Some people do it squatting. I guess that's the way you're supposed to do it?
Yeah, so you work out everything.
Yeah, all right. And you're basically whipping the ropes up and down. And then apparently it's good for you. Trusting is good for you?
Yeah,
Okay.
very.
All right. So amplitude would be physically in terms of that, the battle rope waves, is how far do I bring my arm up? Do I bring it up to here and then down and back, or just a little bit of a wave? So amplitude would deal with how far it is. In terms of sound, how loud I am or quiet I am, that would be dealing with amplitude. Because if I'm getting loud, then basically I've increased the amount of pressure that's hitting your eardrum. Now generically I might use the letter A, but it's really specific to the context of what you're dealing with. And so because it's problem specific or context specific, I can't really give a standard unit for it because it depends on the problem. And I was hoping enough people would be out of the hallway by now. Because high school's over, right? Looks like they're meandering. All right. So what we're going to do, we're going to go up to the hallway.
So with amplitude, the units of measure depends on the problem too.
Yes. Yeah. Because if you're dealing with, say, sound, for example, I mean, sound sometimes is done in terms of pressure, so it would be pascals, or sometimes it's done in terms of decibels, in which case it'd be the amplitude would be in decibels, and so forth. All right, so we're going to head out into the hallway and look at some waves stuff. You don't need gloves. Somebody could actually just pause the recording. Although I do have some recordings out there of so let's talk a little bit about the harmonics and wavelengths and things like that. All right, so basically I'm going to be drawing what the harmonics would look like. So if I have two fixed ends, so ideally the fixed ends do not move at all, they are nodes. The first harmonic would look like that. So I have a node over here, and then antinode. Now, a rope cannot be in both places at once. This is just the way that is typically drawn so that it's very clear that this is the point where it swings the widest. So in the middle, it would be oscillating back and forth between these two spots. So if a full wave looks like that. So that's what a full wave looks like. How many waves is this?
Half.
Yes. So if this distance here is L, the distance between, in the case out there, between my hand and Penelope's hand, L would be a half of a wavelength. So the wavelength in this case would just be 2 times whatever that length is. This is the first harmonic. The second harmonic would be the next simplest wave. It was the first one that I did. It's actually the simplest one out there. but in theory, the second. And it should be symmetrical. How many waves is this?
4.
2.
Oh.
1.
One wave. Looks like that. Again, you're at this position right here, heading upwards, and you go until you get to the same position in the same direction. So this is one wave. So L is just the same as the wavelength.
What's the other curve for?
Sorry?
Is the other one the reflection of it?
It's the way that it's typically drawn, just to indicate that this point is moving back and forth across this whole range here.
Okay. Okay.
The third harmonic.
Is there a limit to how many there are?
Theoretically, no. Physically, yes. And talk a little bit about that when we plot the string vibrator. How many waves is this?
1.5.
Or 1.5.
So L, the distance, if L is still the distance between the ends there, L is equal to 1.5 or 3/2 lambda. Or the wavelength physically would be just 2/3 of whatever that end-to-end distance is. And so notice, and this will actually work for all of them, every time you add a harmonic, you add a half a wave. So the fourth harmonic would be how many waves? And what would the wavelength be
4.5.
of the end in the length? So if you think of a wavelength as just the distance from here to here, and that's 2/3 of the whole length. Or in the case of the fourth harmonic,
It'd be 2.
that's half of it. So L is equal to 2 times the wavelength, or the wavelength is